And so the last lecture of the summer school is by John Rust, who is the founding father of many things, including DSE. So John, we scheduled for an hour and a half. Please take it away.
Okay. Well, yeah, I imagine after like what an intense series.
So now we can't hear you again.
You can't hear me again?
Let me try.
Okay. Okay.
Please keep talking.
Okay, can you hear me?
Yeah. Okay, that's better.
Okay. Is it good?
Yeah.
All right. Well, I'm really sorry I can't be there. I imagine you are pretty exhausted from all the information you've been getting in the last week, but I would have really liked to be there to meet many of you and have questions. But feel free to call out questions because I can hear you and I can see you from here. But I'm going to be talking on a topic. I gave a lecture at Georgetown a couple years ago, and it reflects some recent work. We associate dynamic structural econometrics and all the dynamic game theory with super rational behavior. And the two key parts of that are ability to optimize and then something we call rational expectations or rational beliefs. And so we've seen some ways to get around those assumptions, these strong assumptions, during the earlier lectures, like Michaela's lecture. She talked about subjective beliefs and college attendance. And Victor yesterday talked about biased beliefs of Burger King and its entry decisions. Dan Cow, we talked about our paper about whether a temporary equilibrium, a much less demanding, whether there's a payoff to doing the more difficult calculations for rational expectations. So we're trying to be more realistic in terms of how we describe what humans are doing. At the same time, I don't want to diss the rational theory. In some I worked, like the work that Bertel and Fader just presented, using very, very rational theory. And I don't think there's any general principle that people are rational or not rational. So the question is, it depends on the context. So I'm going to look at three contexts here. Let me see if I can go to the next screen. I'm going to discuss three papers, and in honor of Wimbledon, which is going on, I guess, today and this week, we'll talk about a paper called Disequilibrium Play in Tennis with Axel Anderson, Jeremy Rosen, and Kinping Wang. Then another paper on explaining early bidding in informationally restricted ascending bid auctions. Those are car auctions in Korea, and that's with Sungjin Cho and Harry Parsh. And then finally, a paper that we just sent off for publication called Who is More Bayesian, Humans or ChatGPT? Now, the common thread there is to test human rationality. In the last paper, we're going to actually make ChatGPT another subject. We're going to try to also test how rational is ChatGPT and how does it compare to humans in terms of rationality. So first of all, can we do what Stefano Della Vigna would call, he had a chapter in the Handbook of Behavioral Economics called Structural Behavioral Economics. And you know, one thing you could do is relax optimality, or the other is rationality, or try to do both. I think it's too big of a step to relax optimality. If you're not doing something optimally, what are you doing, right? So in some sense, it gets too ambiguous. So we're going to assume that people can optimize, but when they make mistakes that might be stupid or look irrational, it's because they have the wrong beliefs. Okay, so remember the structure of a model. There's a discount factor, a utility function, and a transition probability. And we're going to identify the transition probability for the states that depends on your action. It's your beliefs. It's your model of the world, how your actions affect future states. So, you know, an example of potentially irrational expectations is you've heard about the vaccine debate. And the people who are anti-vaxxers, and they believe that if you get a vaccine, if you ask your child, you get your child vaccinated, they could get autism. And so there's a measles epidemic going on in parts of the United States, and children are dying because they didn't get the measles vaccine. But the parents believe that actually the vaccine could give them autism. So they have, if you think the objective belief is that there's overwhelming scientific evidence that vaccines don't cause autism, then they're making a very tragic mistake for their child by having the wrong beliefs. So, under rational expectations, people would read the science, they would know what the right effect is, and they would probably get their kids vaccinated. Um, when we talk about estimation, we typically estimate these beliefs from the data or from the best available information so that we can do that in the first stage, and we can isolate those beliefs and then assume that that's what people really believe. The beliefs that we get from the data, which is the same as individual beliefs. And so we only have left the discount factor and the utility function. They're the only unknowns. So if we want to relax rationality, then we have a subjective belief. So we're going to have to infer beliefs from observed actions in general, unless we have data on, we'll talk about elicited beliefs when we get to the last paper. But we're going to have to infer that, and that is a difficult identification problem. So if we just think about this in equations and unknowns, we're going to have a choice probability. This equation right down here is suppose beta star, U star, and P star are the true utility function, discount factor, and subjective beliefs. And we want to try to, they're going to imply a choice probability. We're going to do the dynamic program with the subjective beliefs. We're going to get a choice probability. And for every action and state, we're going to be able to know that. We could essentially non-parametrically estimate that from the data. Now, if we then have we want to see, is that mapping invertible? In general, it's not going to be invertible because we're going to have more. If we think about a finite number of states and actions, we're going to have capital S states because actions add up to one, the probabilities add up to one. We're going to have A minus one actions. So there's the product of the two is the number of essentially equations, and the number of unknowns. Well, there's one discount factor. There's capital A times S possible utility functions, and then the dimensionality of all of the beliefs is S squared times A. So we have far more unknowns than equations. And so to make this really possible, we really have to be willing to make some assumptions. Now, in the problems that I'm going to do today, basically the discount factor is going to be 1. And like in a game of tennis, it happens so quickly, there's no discounting. We also know in tennis and in many other games, the reward function, it's basically 1 if you win, and we can scale it as 1 is if you win and 0 if you lose the game of tennis. So we've now fixed the discount factor and the utility function of the reward, the payoff. We know those. So it's feasible in tennis that we could learn potentially the subjective beliefs of a top tennis player like Djokovic in tennis. So we'll come down and come back to what those beliefs might be, but we'll make them very concrete, and we can actually potentially estimate those beliefs from data under rational expectations. So the bottom line is it is possible, like Victor and others have shown, that we can infer beliefs, but they require us to be willing to make some assumptions. Now, before I get into this, why do we suspect of irrationality? Well, I like this quote here from a guy named Justin Smith. He's a philosopher. He's got a book called Irrationality, A History of the Dark Side of Reason. And he says it's a great paradox of the present age that even though the totality of all human learning is more accessible than ever before in history because of our smartphones, that we can access all this information through the internet and so on, nonetheless, false beliefs are as epidemic as ever. And, you might say, the cost of information, the cost of communication, knowledge is more accessible. If you believe that quote, why could that be happening? And, one thing we have to consider is that all these devices are just flooding information. You probably feel flooded with information right now. Too much information coming in. It's hard to deal with conflicting information. And now with AI and virtual reality, we only have even more problems because you can generate an AI newscaster and complete fake news, and it's really hard to know what's true. We only see the world through our digital lens on our smartphone or our on our laptop. Everything's now coming to us digitally, and humans may be not involved to process that information and that amount of information well. And so if we're overwhelmed with information, we might just latch on randomly because it's too costly for us to process all that information. So that's just a big picture concern. Let me get this. Okay. Let's. Okay, here we go. So I think the grandfather of all of this work is Herbert Simon, and he is a Nobel Prize winner, coined the term bounded rationality. And the thing I just want to point out is this quote in the blue that the idea of bounded rationality is not a new idea. This is going back, and he says by the middle of 1950s. Well, I was born in 1955, and he says that a theory of bounded rationality had been proposed as an alternative to classical omniscient rationality, and a significant number of empirical studies have been carried out that showed actual business decision-making to conform reasonably well with the assumptions of bounded rationality, but not with the assumptions of perfect rationality. So, Simon, I love this quote. There's a picture of Simon. He was born in the same city I was, Milwaukee. A wealth of information creates a poverty of attention. So, similar ideas. Now, the other final big picture point is that, with large language models coming up, just compare that to, you think about their neural networks with billions of parameters or weights. Well, our brain has got connections between the synapses, which I can think about as weights that create our memory, but our brain operates on about 20 watts of energy. Now, it takes relatively a lot of energy for our body weight, 2% of our body weight, 20% of our overall energy consumption, but it's remarkably energy efficient. Now, if you compare that to a large language model, well, maybe we're still in early evolution of these models. It takes about 10 gigawatt hours to train a large language model like GPT, and the daily queries can cost about 1 gigawatt hour in terms of electricity, and that's why we're facing an electricity crisis with large, AI and large language models. So one potential is that, it may be unrealistic to assume that we're perfectly rational because it takes a lot of energy. When we are learning new stuff, we're training our brain, and that requires a lot of energy, just like it takes a lot of energy to train a large language model to process information and refine those weights. So I really like this quote from a review article from 1994 by Hutchinson and Meyer in a marketing journal. And what they give the perspective, which I think is quite true, is that from a broader perspective, one can argue that optimal solutions are known for a relatively small number of similar, well-specified problems, whereas humans evolved to survive in a world filled with a large and diverse set of ill-specified problems. Our suboptimality may be a small price to pay for the flexibility and adaptiveness of our decision processes. So we're using rules of thumb very effectively. We can go on the fly and adapt to things, whereas computers may be less adaptable. Maybe we're not going to be the best player in chess, but evolution didn't really. We weren't involved to do well in chess. So let's just keep that in mind, and let's also keep in mind that when we define rationality, we're not assuming that we're omniscient. So, for instance, you might say today, seeing someone do a rain dance to get it to rain is kind of irrational because, in our state of knowledge, we know that doing a rain dance is going to do anything to make it rain. But maybe 1,000 years ago, for some primitive tribes, given their state of knowledge, the rain dance was a rational thing to do. They believed that there was a correlation between the dance and the rain. So the final general point I want to talk about is that when we acquire information, the standard model is Bayesian updating. We have a likelihood, we have a prior, we observe observations, and we form the posterior probability from that. And we can put that in a dynamic programming. We get Bayesian dynamic programming, and then we have this really interesting exploitation trade-off. It's costly, initially you're uninformed, so you might want to explore to learn more, but exploring is costly because you may force yourself to take an action that is not seeming so promising to learn more, whether it could possibly be a really promising outcome. So you have to explore some paths that turn out to be dead ends, and that's costly to you. And so the question is, how do you optimally acquire new information? When do you spend more time investing to learn more? So in some cases, you can show that even asymptotically, you're not going to learn everything. That, for instance, if you have you're a monopolist and you're learning a demand curve, you're not sure of the parameters of the demand curve, you're going to experiment. But in their paper in 1988 showed that with discounting and optimal Bayesian decision making, sometimes you'll still be ignorant, even in the long run. You'll never perfectly learn the demand curve because it's just not optimal to do so. Now, the final thing here is a series of papers. I put in two of them in the Dropbox. They're theory papers. It's titled Welfare Comparison for Biased Learning. And they consider what happens if you're a Bayesian, but you have the wrong likelihood, right? Bayesian theory doesn't tell us where we get the likelihood. They say there is this potentially subjective prior probability, but the likelihood is generally assumed to be correct. But the question is, what if we don't have the correct likelihood? Well, we have a misspecified or a biased model. And if we are Bayesian with a misspecified likelihood, well, we're going to make mistakes. We're not going to be fully rational. So some of the insights, though, from their study is you say, well, if you were endowed with the right likelihood, then if you agreed on what the reward function is, a person with the right mental model will do better in terms of maximizing their reward than with someone with a misspecified mental model or likelihood. But the problem is that maybe none of us knows what the really true likelihood. There's an inherent ambiguity in the world, and so some of their insights were that misspecified beliefs do not always lead to suboptimal decisions, and we'll see that a little bit later when I get to these papers. And then agents with misspecified likelihoods may actually outperform, or biased people with certain belief biases could actually do better in terms of payoffs than somebody that has got the correct mental model and the correct likelihood, but they have a lot of prior uncertainty. So they're relatively noisy beliefs. They're going to do a lot of suboptimal exploration to get more certain about the world. Okay, so let's start out with an easy one. Let's talk about chess. Do humans play perfect chess? And I think here it's pretty clear cut. The answer is no. If you go all the way back to 1997, there's IBM's Deep Blue. It beat the world champ Garry Kasparov. And ever since then, the world's best players have been computers. And so if humans are really playing Markov perfect equilibrium chess, we can't always be losing to a computer. Now, you could ask then, what about computers? Do they play perfect chess? And the answer is no, not yet. Because, well, there's a theorem by a guy named Zermelo. Zermelo was actually one of the founders of set theory, a mathematician, and this might be one of the earliest contributions to game theory. In 1913, he wrote a paper about alternating move two-player games of perfect information, so chess would be an example, and no chance moves. And he showed that there's only three possible outcomes to these games. It's either the game always ends in a draw, or the first player to move is always going to win, or the second player is going to always win. So an example is tic-tac-toe. That's always going to, if you play it perfectly, it's always going to end in a draw. So checkers has been shown, it's been solved. It's simple enough, and it was solved in 2007. And now we know that checkers is born. Perfectly played checkers will always end in a draw. Now, chess, it's too large for us to completely solve it the way Schaefer did. But there's a measure of performance in chess called the ELO score. And there's a relation. There's an article by Jeremy Ruttman, who, let me show you the scatter plot. The blue dots there are on the x-axis are the ELO scores of human players. And then the vertical axis is the draw rate, the rate of the draws. And then the orange dots, if you see it on your screen, those are computer players. And this dot way up here, that's alpha zero, Google's alpha zero. And so it's way above the ability of human players, and it's trending towards 1. So over time, basically, it looks like as computers are not yet perfect, but they're getting better and better, we're also seeing that when computer players play against each other, they're drawing almost all the time. So not even computers are yet perfect players of chess. Now let's go to tennis, which thinking about the Wimbledon going on. So both are alternating move two-player constant sum games, and like the leapfrogging game that Bertel and Fader were just talking about. So does Zermelo's theorem apply? Well, no, because first of all, there's a significant role of chance in tennis. In fact, we'll see it's got a mixed strategy equilibrium. It's a completely mixed strategy that your behavior will be randomized, and that's going to be essential to our testing strategy. And then, both because of strategic reasons, and then there's imperfect muscle control, right? If you slam a ball at 140 miles an hour, sometimes you're going to hit the net, you're going to fault your serve. And then finally, there's no possibility of tie, that the rules of tennis are going to only lead to two outcomes, either the server wins or the server loses. Now, the real challenge here when you analyze something like tennis is we want to separate brains from brawn, right? So we want to say what part of tennis is mental and what part of is it physical? Someone like Djokovic or Alcaraz, how much is it their superiority just because they have a stronger serve and their ability to play on the court? So we want to actually develop a theory that we can separate these two and control, and we're not going to assume that Djokovic is going to be a better server or it's going to fault less. We're going to just say, what could he change certain things that he can control with high probability? So that's what our paper is about. So we want to test whether our behavior, the behavior we see in tennis. So we have access to a huge amount of data on the web. There's something called the tennis charting match charting project, and you can surf all of the data and download it. People actually every tennis match record in great detail what happens at every serve in a tennis game and every game within a tennis match. And so we're going to look at that, use that data to test behavior. Now, you might say, why are we doing such a simple case? Well, if you look at a firm, it's much more complicated because we don't know always what the firm's objective function is. You might say, well, isn't it maximizing discounted profit? Well, not always clear, because if you're a publicly traded firm, your firm has a market value, and the work of Campbell and Schiller and others shown that the market value of firm is often not equal to its present discounted value of dividends. So there's some kind of difference, big gaps between what the market values of the firm is and what we would calculate as a discounted value, which we typically use in IO and a lot of economic theory. So if you're actually looking at a CEO, they actually have their own mental model of how the market reacts to their actions, and they may not take an action that I've actually met with CEOs who explain they don't think the market could really evaluate well. It's a new strategy may not be received well, and it could actually hurt their market value. So when we look at tennis, where we know the objective that you want to win, now maybe if winning for Djokovic, that's he's got a big utility. He wants to win, I think his 27th major title. but he also will have millions of dollars. But it's really winning is better than losing, so we want to think about him as maximizing the probability of a win. Now we're going to build on conventional wisdom and the early work on this, going back to 2001, a paper by Walkers and Wooders in the AER, Minimax play in Wimbledon, and they looked at individual serves, and they conclude that servers were randomizing, and they tested an implication of mixed strategy equilibrium, which is if you're playing a mixed strategy equilibrium, every action that you're mixing over, you should be indifferent. Now, indifference in this case is the probability of winning the point should be the same if you serve to wide or serve down the tee. And so they got data from Wimbledon and tested that hypothesis and unable to reject that the probability of winning a point in tennis is the same for each possible serve direction, which is something that really good server like Djokovic, they absolutely have control over what direction they serve. They just randomize that as part of their strategy in tennis. So let's just recall for those who don't know tennis. Remember tennis, there's a tennis court, here's a singles court, and in any given game, one person, would say Djokovic, will be server for the entire game, and the serve alternates the direction between the ad court and the deuce court. So the first serve is from the ad court. It's got to go over to that black dot is in the receiving area. The net is right down the middle, and so that would be a wide serve is toward the edge of that box. And then when he gets after that first serve, he goes to the deuce court and refers, serves to the opposite box, and in a wide serve now will be to the other side. So we're going to standardize this. We're going to look at from the point of view of the returner. The returner is standing somewhere behind the end line of the court to be able to reserve the ball. And so we can basically see the direction of the serves, whether we're going to call them left from the returner's perspective or right. And so that will standardize. Left and right will be the same, whether the serve is to the ad court or the deuce court. And then a body serve is going to be somewhere in the middle. It's basically trying to aim so the ball bounces and hits the returner close to the body, making that harder for them to return. So here's if you think about the entire, it's called the service game. A service game is based on points. And so, love all is the first point. The circles there are first serves. The rectangles below it are if you fault your first serve, you go to a second serve. So if you made your first serve there's a rally and you won the point, then your score goes from 0-0 to 15-0. We've numbered these points with odd numbers, 1 to 3, or if you lose the point, if the server loses the point, they go to state 9, that's 0-15. So this is going to play a role in what we're going to do to write down a mathematical model of tennis. And then the second serves are all going to be even numbered. Now, the way that the game goes then is that points, stochastically move in this game, and there's two absorbing states. You either lose or you win, and that's going to be states 37 and 38 in our notation. And then there's something called the deuce endgame. So you can get down to a tie at the very end of the game. Let's when you got essentially 40-40. And so once you get to deuce endgame, you've got to win by more than 1 point. So if you're at deuce and you win as a server or as the returner, you go to add advantage in, and then if you were to then win again, then you would win the game. But if you had the advantage, but you're going to have to win by 1 more point. But if then the returner won that point, then you go back to deuce. So you have to keep circling around. So this is not a completely directional game in the term of Federer, because we have this essentially infinite loop, and potential you could be in deuce in the deuce end game for an infinite amount of time, but in practice it always ends in a finite amount of time. Now here's the individual. So each of these, the red, the blue dot and the second serve, if we expand on that, here's the first serve. Now here's what's going to happen. And the first serve, either the serve could be in or you could fault it. So we're going to let pi represent the probability of faulting or getting in on the first serve. 1 minus pi is the probability of fault. And if you get conditional on getting it in, then you're going to go into a rally. The ball is going to be hit back and forth over the net. And so now we're going to have a separate pi for winning. So conditional on being in and that there's a rally, pi of win is the probability of winning that point. And with 1 minus that probability, you lose that point. Now, if you fault, you have an option value for the second serve. So in the second serve, again, you have a probability of going in, or you have a probability of what's called a double fault, 1 minus pi, you would have a double fault. And if you go in on the second serve, then you could either win the rally on the second serve or lose the rally. And so based on that outcome, then you're going to transition to the next point in the tennis game. So these are, we call it the point stage game. It's a sub-game of the overall game of tennis. And a service game is a sub-game of a set, and a set is a sub-game of a match. So it's a very complicated hierarchical structure. We're going to assume that the objective, I'm going to focus on an individual service game, and if you maximize the probability of winning every service game, you're going to maximize the probability of winning the set and therefore the match. Now, we're going to get different results than Walkers and Wooders. And this graph explains what's going on. Now, what we have is the red line here is the point win probability, and then the vertical axis is going to be the game win probability. So for a point win probability, that's just the 45-degree line. So let's imagine you were equally matched. You had just a 50% chance of winning as a server, and that was the same at every point in the game. So let's go back to this diagram. So at every point, you could either go here 15, 0, or 0, 15 with 1/2 probability, and all the way down the tree. Well, then what you can see is the tennis game would really be like a random walk, which has a half equal chance of going left or right. And as you go down through this game and play it out, you're going to absorb either a win with probability 1/2 or lose with probability 1/2 because of the properties of a random walk. Okay, so that's where this blue line is the game win probability, and at 50%, the random walk, that's the same as the game win probability. But now suppose that you could increase your chance, you were just a little bit better server, and your probability could go up to 51% probability or 55%. Well, because now you have a random walk with drift, and that happens at every point in the game. If you're a little bit better at every point in the game, you're going to have a much bigger chance of winning the overall game. So a little bit of improvement in every point translate into a much bigger magnification in the probability of winning the overall game. So we're going to call that the magnification effect. And this is what we're going to exploit. By looking at the overall game, we're going to be able to detect. See, Walkers and Wooder, maybe, a variation in serve direction only changed the win probably a small amount for an individual point, which is hardly statistically detectable. But when we look at the effect on the overall game, a small deviation by serving more to, say, your right than to your left could at each individual point might have a small effect, but it has a much bigger effect on the game probability, the overall tennis game, and we can detect that. So there's two key implications. So for these structural models, we get game theory provides very strong implications. It should be that if we look at a server in a game, because it's a mixed strategy, they should be indifferent between every direction that they serve, and they have control over that. So that means that the payoff is in terms of the probability of winning the game. So the probability of winning should be independent of the serve direction. And then related to that is what's called the one-shot deviation principle. if you are playing a mixed strategy equilibrium, and if I deviate at any time, it's not going to be able to be, my opponent won't be able to detect. If I suddenly start serving just to the left instead of mixing over that, my opponent won't really realize that. They will keep playing to behave the same, but it shouldn't be the case that I should be able to gain a higher probability of winning the over game by deviating from my mixed strategy equilibrium. So these are very closely related concepts, but they result in strong testable implications for tennis. So let's go back to the model of the game. We're going to have these score states that we talked about in the picture, 1 through 38, where 37 is win and 30, and these are the absorbing states. You either win or you lose. The even number states are going to be second serves, and the score state's going to be numbered in a way. And now let's talk about what the server and the returner choices are in tennis. Now, there's actually more than these, but let's just think about the server serving at each point. The server chooses a serve direction. That's going to be D. And we're going to just model that serve direction as 3 choices, left, body, or right, LB or R. And they also have a choice over the serve speed and the serve spin, okay, because they can put spin on the ball. Now, we're not going to, in our data set, we don't observe spin and speed. So we're going to assume that we're going to just focus on the serve direction. When they're mixing, they could be mixing over all of these things, the direction and the speed and the spin. Sometimes they put spin, sometimes they don't. Now, the returner, we can think of this as, even though the server serves first and the returner has to return, the returner has to devote mental energy to where they think that ball is going to land. Is it going to go left? It's going to go right or into their body. So they're going to have to devote mental energy to focusing where that is, but they may be randomizing over where they put their attention, knowing the server is randomizing. Now, finally, we're going to add something called muscle memory, because there's evidence in tennis that there is serial correlation in serve. So Walkers and Wooders assume that a perfect mixed strategy should also be serially uncorrelated, and they found some evidence that there was serial correlation in serves. Now, we're going to show that you could have a perfect mixed strategy for the game as a whole if you have a muscle memory. Now, muscle memory means that if you serve to the left, your body remembers that in the short term, and you have a slight preference because you feel like serving to the left, you got the last one in, you were able to serve 140 miles over the net, didn't fault, and serving the same one, you just have a better chance of doing that. So we're going to, since the serve alternates between the ad and the deuce court, we're going to remember the last 2 serve directions, and the muscle memory state is going to remember the last 2 serve directions. So I don't want to make a big deal given the limited amount of time, but we're going to allow that, and we can have a model of game theory where this could allow for serial correlation, yet it's entirely consistent with a mixed strategy. So we would have mixed strategy, a Nash equilibrium or Markov perfect equilibrium of tennis with some serial correlation across points. So we don't want to reject it because of serial correlation. So now here's our definition. We're going to call these things point outcome probabilities. These are going to things that we could potentially estimate from the data. Now there's underlying things. If we don't observe speed and spin, let's let rho be the mixed strategy of the server over speed and spin of the serve. We observe the point state and the muscle memory state in tennis, and then they have a strategy L for the direction and or a probability of getting making the serve as a function of all of these variables. We integrate out what we don't observe, and what we have is now a probability that the server gets it in, does not fault, as a function of the score state, the muscle memory state, and the serve direction. And then similarly, if they get it in, then there's going to be a rally, and we're going to summarize that by just this conditional probability. What's the probability that if the serve is in at score X and muscle memory state D, and you served to direction D, that the server will win the rally that comes about? So now we have these 2 probabilities that we can potentially estimate, and if we're going to assume rational expectations, we could take this huge amount of data from the match charting project, and estimate these probabilities, these pops, and then test directly whether whether there's equal win probabilities using these. These are essentially the beliefs, right? If you had rational expectations, this is, Djokovic he should know the probability that he gets it in as a function of his serve direction, and conditional on getting it in and going in a rally, if he's facing, Nadal or somebody or Alcaraz, then there's going to be, he's got a rational estimate of his chance of winning that point. So now let's think about how dynamic programming comes about. We're going to define the server's win probability. So the subscript S is the win probability of the entire game if you're in score state X and muscle memory state M. So there's going to be a Bellman equation for the win probability, just like there would be any other kind of a dynamic program. So it's going to be just the maximum, it's going to be maximum, this is going to be the choice-specific value function, right? This is the conditional probability of winning in score state X and muscle memory state M if you serve either left body or right. So the question is, if we can estimate that win probability, then we can test that we should see if they're in a mixed strategy equilibrium, these win probabilities should be the same independent of the serve direction. Now, let's break it down. If you're in score state X, so like 0-0 love all, then you could either go to 15-0, or if you win, you get 15-0, or you lose that first point, you go to 0-15. So these are the successor states in our numbering convention for the game of tennis of a win on a point or a lose on a point. So we can write down recursively the win probability is, well, the first one is you get the serve in, you don't fault, and given the rally that follows, you won that rally, then you won that point and your score state goes to 15-0 and your muscle memory gets updated. The other possibility is you could serve that point in, but you lost the rally. Well, then you lose the point. And the third possibility is, well, you faulted. Now, if you fault, you don't either go to a win or loss. You go to this even number state, because remember, X is 1. Now you go to state number 2. That's the second serve option. And then now at the second serve, now there's no more, you don't have any further option value. So either you get the serve in at the second serve and you win the rally and you win the point, or two things could happen. You got the serve in and you lost the rally, or this is a double fault. You fault again on the second serve. And the top tennis players, they don't like to double fault, although that does happen. So now we have the entire dynamic programming recursion. We can do dynamic program and we can solve this game. If you give me these are like the beliefs. And if we assume they're rational, we could estimate these from the data, then we can actually estimate these win probabilities. In fact, so then in Nash equilibrium, we can estimate these win probabilities. If we had enough data, we could estimate them non-parametrically, because these are all discrete states. We just look at all games starting in state X in muscle memory M. What fraction of them do you win from that starting point if you serve left, right? And then, so you could get non-parametric. The problem is that you don't have enough games to estimate these non-parametrically, but we could then, test these three restrictions for a mixed strategy Nash equilibrium. Now, what we're going to do is potentially allow for disequilibrium or suboptimal strategy. So P is like the CCP, right? It's your choice probability of what direction do you serve to in state X and muscle memory state M. And so here we have this equation. Now we're going to have a value function, a win probability conditional on direction, and the analog of the Bellman equation, where before it was the max. Now, if you follow a potentially suboptimal strategy, you may not put all your mass on the highest win probability. You're going to get an average win probability for a potentially suboptimal strategy. And now what we want to do is see, can we value that win probability? And in fact, yes, we've been seeing that in this course. There's something called policy iteration. So here, equation 1 is like the policy iteration equation for a dynamic program, like an infinite horizon stationary dynamic programming. So we think about the wind probability as a long vector, 298 by 1 for all of the x and m states. And the little w here is the probability of winning outright, right? So it's either going to be 0 or 1, and most states it's going to be 0 because, for instance, go back to this picture here. If we go back to this game tree, there's no probability at any of these points. You can't directly go. But at 40-15, you could directly win, and you could make a transition to winning, okay? But in many other states, and then here, you could make a transition to losing. So we can write down all those transitions and those probabilities, and then this M is going to be a transition. It's going to be a sub-transition matrix because the probabilities are not going to add up to 1, okay? Because some probabilities are going to be absorbed in, you go to the absorbing state. So what's going to imply is we have a linear equation system, and it's going to be my win probability is going to be a function of two things. It's going to be a function of pi. Those are the pops, my probability of winning a rally, the probability of getting not faulting the serve, and it's going to be depending on my serve strategy. And if I can estimate these two objects, I can solve equation 1, and I can estimate the win probability for every possible direction. So that's going to be 894 conditional win probabilities that I can estimate from the data. So here, let's just show you how this works. Let's take Federer serving to Nadal, or Nadal serving to Federer. The NP and non-pair, if we look at all games in the match charting, there's thousands of them, of Federer serving to Nadal. Federer would win about 79.6% of them, and there's the standard error right there. Now, if we use this equation 1, and we estimate instead the p and the pi and find out the inferred win probability, we call it the reduced form estimate. That's pretty close. They're within a standard error. And if you look down, we can basically rely on pooling the data, like we're going to be able to pool the data on pi and p efficiently, and then estimate this win probability at every stage of the game tree. Now, to also check it further, at the very, obviously at the very top of the game tree, that's where we're going to have most observations. So then we have enough games where we can say, well, how many games where Federer served left on his very first serve in the entire game did he end up winning? Well, he won 81.6. But on the body serve, he only won 65%. So that doesn't look like equal win probabilities, right? He's like left and right, he's winning 80%, but he's only winning 60%, 65%. Now, the problem is you might say, well, maybe he served very few body serves on the very first serve in the entire game, which is true. So our estimate is much smoother. It looks closer to equal win probabilities here. And it's because it's not as susceptible to small numbers of observations in any given cell of the game. So we have a more reliable way of estimating conditional win probabilities. Now, when we do that and do the test, well, first of all, we could form a chi-square test. We can solve, test for these conditional. We have 894 restrictions on the win probabilities in all of these states simultaneously. And when we do that, we just blow away the hypothesis of equal win probabilities at every stage of the game of tennis. Now, if we look at smaller numbers of states, it should hold also at any given point, like the first point of tennis or any given point. And we get these are p-values, we get strong rejections. Now, for some states, the p-values are, above 0.05. We don't get rejections. But basically, the first thing to take away is we can blow away game theory, the assumption that these players, even the very top players, are playing a perfect mixed strategy equilibrium. Now, if that's the case, yeah, question.
So I guess to some extent, the tennis player themselves must have like a bigger, observe more states than we do. So So I guess you'll be sort of ignoring some latent states when you set up the game. How does that affect your estimates?
Yeah, you're right.
For example, the player, I guess, knows like he's got a bad day or a good day, or is that I don't know. So there must be a lot of variables that the players take into account that your model ignores. So I don't know how does that affect the results?
Yeah, Dennis, that's an excellent question. Obviously, maybe Djokovic is having a bad day. Maybe he's got a sore shoulder. So, and also might be an energy budget. You might say he gets tired. We're going to assume, we're going to ignore, for instance, the energy budget. We say within a single game of tennis, we're going to assume these guys are not getting tired. And if there's an injury, you could be playing worse and your opponent might know it and try to play to your injury. We did a number of tests for stationarity. We tried to see if there are games where we could see where one of the players were injured or public information, and did we see different kinds of outcomes in those games. And generally, we're not able to reject stationarity, that the behavior, there doesn't seem to be persistent state variables that are causing them to play differently. Now, over huge amounts of time, over 10 years, Djokovic may not be as fast as he was 10 years ago. Probably he's not. So what we did is try to group the data into smaller intervals where we could see that we could not reject the behavior of stationary play. And even though there possibly private information we can't observe, we have an argument at the end of our paper that that even if there was stationary, if we're able to reject stationary equal win probabilities in this full information game, then it should also indicate that there's a failure of a Markov perfect equilibrium in the game with more information, with private information. So I'll leave that. I'll refer you to the end of our paper, or we make that argument. I want to go into it now. So we think we have a good argument to that, and that the results are credible. Now, let's just go to this, and then I'm going to switch to the next paper. But once you can reject the hypothesis, they're equal win probabilities for every serve direction, there's going to be one direction that's going to have a higher win probability. So if you use the computer science term, you want to follow a greedy strategy. What's a dynamic program going to do? It's going to you're going to solve the entire game by always going to the direction that has the highest win probability, is computed using these estimated pops from the data. And so now we can say, given the actual serve strategy, which is a mixed strategy, it can't be optimal because we're seeing deviations. A deviation strategy will be a pure strategy. Now it's a one-shot deviation. So you might say, if you consistently play a pure strategy, your opponent will react and change their behavior. So we're going to be testing a hypothetical. If you made a one-shot deviation, how much could your win probability go up? Now let me show you this picture. Now the one thing we want to do is we want to be fair to these players. Now when we're estimating the pops, we are using data, and there's noise in those data, right? We don't have an infinitely large sample size, so we don't know what the true pops are, just like Djokovic and the other players may not know what they are. They're using data as well, just like we are. So what we're going to do is when we estimate the pops, we're going to use the asymptotic distribution of the parameter estimates to generate 500 randomly distributed pops around the point estimate of the pops. So we're going to get a whole distribution of pops, which is a whole distribution of behavior that could be, you can think about them as alternative pops that we might have estimated under different data sets. You could imagine doing bootstrapping or other ways of doing the same thing. So what we get now is an entire distribution of win probability. So the black curve is the reduced form serve strategy. So we estimate the actual serve strategy of Nadal serving to Djokovic. He's the server of all games he's serving to Djokovic. And now as we vary the pops randomly, we're going to get a distribution of win probabilities. And the median of that is about 70%. So he's got about a 70% chance of winning any game when he serves to Djokovic. Now, what we did is estimate a dynamic programming model with subjective probability. So what we do now is instead of using the objective pops as our point estimate of around which we're randomizing, we estimate a likelihood where we reveal the subjective beliefs. So we use the data on their serve strategy to uncover what Nadal really thinks his beliefs are. So we're going to call those I don't have time to go into detail, but we're going to basically now estimate those beliefs as structural parameters with a likelihood function. And now we're going to take those subjective beliefs and we're going to also perturb them around the asymptotic distribution. And what we see is these two distributions are almost identical. So what this means is that our structural DP model with subjective beliefs is going to be basically, it's giving almost identically the same serve strategy as what we would estimate from the data. And so that when we look at many counterfactual perturbations of what the pops might have been, the relative strengths and weaknesses, they're going to generate the same kind of behavior. So we have a good structural model of Nadal serving to Djokovic. But what we find is that his subjective pops are too, in some sense, pessimistic. They're distorted. That in order to rationalize his mixed strategy behavior, his serve strategy, we have distorted pops that are different from what we call the objective pops that we can estimate from the data. So we have objective pops and subjective pops, and they're different. We find that they're different. And the subjective pops can rationalize his performance in the game. But now we can say, okay, suppose we were to change his behavior and let him solve the dynamic programming problem, but using the objective pops. So instead of using his distorted subjective behavior, how well would he do? And that's given by the green. If we solve the entire dynamic program for the game with the reduced form pops and we perturb them, we're going to get a distribution of win probabilities. And at the median, there's a huge increase in his probability of winning against Djokovic. So in other words, there's a deviation. His beliefs are distorted about his own strengths and weaknesses in his ability to fault to serve and his ability to win a rally against Djokovic. And that when he were to adjust his beliefs, his probability of winning the game would go higher. And this would come entirely from just his change in the serve direction in a one-shot deviation. So, you might say this is a massive increase in the probability. Remember, this isn't a long-run prediction. It's a one-shot deviation, but it's enough to strongly reject game theory prediction. Now, the other red line here is a myopic serve strategy. Now,
There's a question, John?
Yeah, question.
How can you differentiate between his beliefs being wrong or him having private information that you're just not privy to?
Well, I don't know if we can at this point because we'd have to take a stand on what there is private information. It's IID. It's a traditional idiosyncratic shocks, which we estimate when we estimate this model. Those are very, very small. There's essentially none. To get a mixed strategy, we found that we have a sigma parameter on the or we call it lambda parameter in this paper on the magnitude of the shocks. And they're essentially almost zero. So it's almost like this model is perfectly fit. There's no random private information. But if we have persistent private information, I can't answer that until we actually put it in. And once you put that in, the model is going to be we don't know how to solve it. Because then you're going to have Bayes' rule. Basically you'll have beliefs about your own performance in the game. And maybe you wonder, is your opponent hurt or are they lagging in the game? And you're going to have carry around a posterior distribution of those beliefs. And we don't know how to do that. So the honest answer is we don't know what difference that would make. But in general, we can do this for many other players. You can say this complete information version. And what we find is that the better the players are, the probability of the server as it gets closer to 1, the gains that we can get from adopting irrational expectations get smaller. But for the worst servers, where their probabilities of winning as server is closer to 50%. Now, part of this, is mathematically, you can't have a probability greater than 1. So if you already have a 90% chance of winning, you can't increase your winning probability by more than 10%. But for these other players, the less elite players, we see very big gains. Now, you could be, I encourage skepticism. You say, wow, this just seems too big to be, these are really professional players. But some independent evidence of why, we may be right here is that there are firms called Tennis Analytics that make big money selling advice to the very top players. They collect data, a huge amount of data, much more data than we have. They have the speed and spin. They have dynamic replays of the entire game, including the body motions of the players on the track. They do extensive analytics and statistical analysis of the plays of the game, and they find that they earn a lot of money precisely because the players feel they can learn something. They're not providing coaching advice, how to fit, they're giving more strategic advice. Where do you serve at different parts of the game? So if they were playing perfect tennis, these firms, these tennis analytic firms, and we met the owner of one of them, and he agrees that our results, he thinks that they're not going to survive in long term as the returner adjusts. But, basically he says, absolutely, I'm making money on my business because these guys are not playing, they're not perfectly rational in how they play the tennis game. Okay, any other questions? I'm going to move on to another paper, and hopefully I can provide more convincing evidence. If you're skeptical here, maybe you say, well, maybe there's persistent private information in the games and that could explain it. I would have to say, I don't know at this point.
There's a question.
Yeah.
Yeah, my question on the having additional data thing, could you make some more progress? It sounds like there's a couple mechanisms. There's like, you could be trying to control the beliefs of the opponent, or you could also be like, you'd have some physical limitations or something like that, like more data about like when their win probability is especially low for serving at the body might be informative. Like if it's something about hot days or something about new athletes that they're playing against or something like that, that might help disentangle these mechanisms.
Well, we do condition on individual, like we said, Djokovic and Nadal. We also condition on grass and clay courts and hard surfaces. We didn't look at the temperature at the time. We could do that. My suspicion is that we got very similar results, whether we condition on hard courts or clay courts. Like you might say, Djokovic is better on a hard surface than he is on a clay court or something. And so that certain players have an advantage on certain types of courts. So, we would find the results to be somewhat different, but they didn't overturn the idea that we could see deviations and that by adopting more rational beliefs, their beliefs seem to be distorted and they could increase their win probability by using that information. Okay, so I'm now going to turn to this other paper on auctions that I was originally scheduled to present. I'm going to go into the other room here. So getting a little hot outside. Going to get in the air conditioner. I'll be a wimp here. So this is, so how am I doing for time? I've gone 1 hour and so I have 20 minutes. So I think I only get through 2 of these. The other paper is at the end of the slides. But we're going to look at car auctions in Korea. Now, again, these are professional bidders. So what we've gotten data from a car rental company that is selling thousands of cars every month in Korea. And the people who buy these cars are auto dealers, and they have professional bidders that come to the car auctions to buy the cars, and then they turn these rental cars around and resell them to consumers. Now, the car rental company thought that there was collusion. They used to sell these cars in open out ascending bid auctions at each rental location. And they felt that the car dealers, the bidders from them, were kind of being a little bit too close to each other and maybe colluding before the auction. So they decided to create an online dynamic auction So the other ones were, ascending bid, do I hear 5,000? Do I hear 5,500, right? Going, gone. So that's called an open ascending bid auction. So they tried to recreate that same kind of auction, but online, and we're going to call this design the Korean auction. Now, the really interesting thing, though, is instead of the traditional oral outcry auction, the 2-minute online auction suppressed any information about the other bids during that 2-minute auction. You only know at any point in the auction your own bid, your own high bid during the auction, and whether it is, whether your bid is the highest among all bidders. And at the end of the auction, whoever had the highest bid at the end of the auction wins the auction. Okay, so this is why they're informationally restricted. You can only see your own bid. You don't see what everyone else's bid. That's really different from what they call a Japanese auction, where all the other bids or the English auction, where all other bids are publicly seen by the other bidders. So you don't even know, in fact, how many other bidders are playing, because you only see a screen, and you can think about a little red light at the top of the screen, and when it's red, you're the high bidder. If it turns off, you're not the high bidder anymore. And you see how much time is left during the auction. So it's a kind of a boring auction to participate in. So the reason they did that is they thought that we're going to prevent any kind of collusion by signaling bids during the auction. And so we're going to get less collusion, and we're going to get higher bids for our cars. Now, it turned out Bob Miller has, there was a similar auction design chosen by Texas banks, or certificates of deposits, where the information was similarly censored. And they have a paper in 2021 that analyzes this. And this is a quote from their paper. The market features frequent jump bidding and winning bids well above the highest losing bid, suggesting standard empirical approaches for ascending bid auctions may not be suitable. And so they found a lot of information frictions in these auctions, and we're going to find something similar. So let me show you 3 examples of auctions here. So the x-axis is time from 0 to 120 seconds. That's how much time. The auction ends at 120 seconds, 2 minutes. And the red line is the high bid track. So to be a high bidder, you have to be on that high bid track. So the first auction comes in by bidder B11, the star, at about 20 seconds, and they're the high bidder. And then you see they make a rapid succession of bids, but then just after, the bid 28 bids higher. Okay, so now they have the high bid. Now look at the diamond. Now that would never happen if there was complete information. Why would you bid below the highest bid, right? You would maybe not bid at all. But the reason the diamond bid there is they didn't know what the high bid. So they're making a stab. They want to trying to find out. So they're bidding around 3,000, and they find out, well, I'm not the highest bid. And then you see this bidder 5. They're creeping, right? They start out with 2,200 or something, and they start methodically creeping until they stop when they get to be the high bid. Okay, so all of these is behavior that's perfectly reasonable. They're sending bid auctions in an environment where you don't know what other people are bidding, right? So you're learning, and this is a perfect example of dynamic learning in an auction. And then you see in some auctions behavior, what we call sniping, right? So the winner of this auction here was B3, the red dot, and the red dot made only a single bid in the entire auction right at the last, at 118.125 seconds. Somebody came in just after, but they weren't quite as high, or being second also, whoever's first, they get time priority. And so this bidder, the sniper, won the auction. So again, you might say that looks pretty reasonable. Maybe game theory could predict this. Well, let me show you something where it looks pretty irrational. Okay, now take this auction. In this bidder here, the diamond, bidder 28, in the first second bids 14,690. And, you know, he stops bidding the entire, or she, there's just this one bid. And look at all these other bidders. They're furiously trying to learn what the high bid, and they're all trying to creep up, and they're all stopping well below 7,000. They don't think it's worth more than 7,000. Well, you know, what's wrong is maybe this person has a special deal and they really think it was worth maybe 20,000. But if the person also did more of a gradual learning strategy, they bid early and they overbid massively, right? If they started lower and higher, they're willing to go above any of these. They could have gotten this thing for more like less than 8,000 for sure, and probably, you know, like 7,500. So, you know, that's just patently not reasonable behavior, right? And then here's the kind of crazy bid. There's some person, see, in the auction off, you're always liable for your highest bid so far. So, you know, this bidder here, 11, is zigzagging. They're, you know, maybe they're bored or something, but they have a high bid and then they really reduce it. Well, there's no signaling value because nobody else sees your bid, and you're liable for your highest bid. So there's just no reason to put a lower bid, right? Okay. So, yeah, question.
Can you take one picture before, so one slide before?
Can you
So-
go one back to?
Go to the previous slide, please.
Oh, yeah, go back, yeah.
Yeah, I'm thinking because this is ascending auction, right? So basically, the winner does not pay their own bid, they pay the second highest bid, right?
No, it is the first, it's like a first price auction. The highest bid wins the auction at the bid they pay. So this guy bid 14,690, and that's what they paid.
Oh, okay, thank you.
Okay, so it's a dynamic first price auction. You know, you could imagine it was a second price auction. So we see these different kinds of behaviors, and what we're going to show is, you know, these are the most obvious cases I can show you of kind of irrational behavior. But we're going to show that even among these people who are creeping, there's a lot of bidding, like over here, the red dots, they're just too early and too high to be rational. And that we think that basically in game theory, we're going to argue, should predict that everybody should just wait to the last second. Everyone should be a sniper. So in the time I have left, let me see if I can convince you that what we call a perfect Bayesian equilibrium, in a perfect Bayesian equilibrium, nobody is going to bid early, okay? Now, basically, when you're a perfect Bayesian equilibrium, it's a very, very difficult object to compute. Because first of all, you know, we're going to introduce, you know, the paper introduces an alternative, simpler equilibrium concept called anonymous equilibrium, which is perfectly tailored because everybody really is anonymous. But the natural, you know, heavy-duty game theory concept is a perfect Bayesian equilibrium. Now, in a perfect Bayesian equilibrium, think what you have to have. You have to have a prior over how many other bidders could enter your auction, and you have to have a prior over all possible valuations, the distribution of the valuation, the valuations your opponents might have. You know your own valuation. So you have to have these massively high dimensional prior over the number of bidders and all of their valuations. And then as you proceed in the auction, because of the coarse information, you have to make very subtle, you know, decisions like, should I bid in the first second? If I bid in the first second, then, and I'm not the highest bidder, what do I deduce about the other bidders? How much did I learn? Now, it seems like you learn very, very little, and that probably is true, but still working out what a perfect Bayesian equilibrium is really hard. Now, what we can though say is there's going to be multiple perfect Bayesian equilibrium, and if the auction has what we call a hard close, in other words, it stops at 120 seconds, and doesn't go on or doesn't stop early, it's hard closed at 120 seconds, you can think about this, there always will be a non-informative, an uninformative perfect Bayesian equilibrium where everybody snipes, okay? So basically a first price auction, a Bayesian Nash equilibrium to a static first price auction will also be an uninformative perfect Bayesian equilibrium of this dynamic game. And why is that? Well, because no player expects there's any value to bidding early, but every player is forming a best reply to their beliefs about everybody else in a standard first price auction. We know that exists, so there's always this uninformative perfect Bayesian equilibrium. Now the question is, are there other perfect Bayesian equilibria which are informative? In other words, are they going to could it be that in a perfect Bayesian equilibrium, you do bid early and you learn from that, and that is going to be an alternative equilibrium? So now we're going to, let me show you an example of a simple two-period, two-bidder example where we can show that there's only an uninformative equilibrium. So let's think about backward induction. So there's two bidders. They both have uniform valuations on the 0-1 interval. And in the second period, if it was a static first price auction, what you can show with uniform valuations is the black line is they're going to be their equilibrium bid function. They're going to both bid their valuation over 2. That's going to be, if they were both sniping and that was the equilibrium they're playing, then they would bid V over 2. But now consider, is there a informative equilibrium where they're going to bid in period 1? So you have to work by backward induction. They have to find out in period 1, if they both place bids, one of the bidders is going to learn that they're the high bidder, and then the other bidder is going to learn they're the low bidder, right? So that means that after the first stage, once they place those bids, the second stage of that auction, the second period and the last period, is going to be an asymmetric auction, right? You're not going to both think that we both have uniform 0-1 valuations anymore. One of the bidders is going to be a strong bidder. In other words, the strong bidder is going to know they have the higher valuation, and the other is going to be a weak bidder. They know that they didn't have the high valuation, so they're going to be facing somebody who values that car more than they do. Now, the red and blue line are the equilibrium in that second stage auction. So when you have this induced asymmetry, the blue line is the valuation for the high valuation or the strong bidder. They know they don't have to bid as strongly to win the auction, and so they bid less for any given valuation than the weak bidder, right? Now, let's now think about this. If you had bid in the first period, and who would you rather be facing? Would you face the blue line or the red line? Well, clearly you'd be rather facing the blue line, right? Because they're bidding less aggressively. The strong bidder is bidding less aggressively to win the auction. Well, how can you ensure that? In the first period, you'd say, well, I want to face the blue line, not the red line, so I'm not going to bid in the first period. Then I'm going to fool my opponent to thinking they're the high bidder. They're going to bid less aggressively in the second period, and I'll get and I could still win the auction for less. Well, of course, if they're both rational players, they're going to both come to that conclusion. They're both going to realize there's no purpose for them to bid in the second period. It only makes them both worse off. So they're both going to stay out the first period, and they're both going to realize, well, if we're both staying out in the first period, there's nothing to be learned in the first period. So the second period is going to be like a virtual single shot first price auction. They're going to both bid according to the black line. So that means this uninformative equilibrium is the only equilibrium to this auction. Okay, any questions to that? Now let's just go to a concept of anonymous equilibrium. And then I'm going to stop. I know you guys are tired, so you know, and you probably have to catch airplanes and everything. So thanks for listening to me talk on. The papers are all in the Dropbox if you want to read more. We're going to relax rationality a little bit. So in this paper, what we're going to do is we don't want to make the bidders stupid. We want to see what's the smallest relaxation of perfect Bayesian equilibrium that we could use. And we have a concept called anonymous equilibrium. Now, let's illustrate an anonymous equilibrium is that, let me show you a picture here. Basically, we can estimate, well, let's go back to these pictures here. When we look at all these auctions, what we see is an ascending pattern of bids, and we see these high bid tracks. So we can think of these high bid tracks as stochastic processes in bids over time. From 0 to 120, there's going to be a random bid. At any point, it's going to be the highest bid. And what we're going to assume that this stochastic process is known to all the bidders. So it's like a rational expectation. It's like by participating in many of these auctions, you're going to have a pretty good idea at 40 seconds for a standardized kind of car, which is called this Avanti. We see lots and lots of auctions for this kind of car. They're pretty standard generic rental cars. You're going to have a belief about the high bid in the auction at every second in the auction. So now with those beliefs, you can think about solving a dynamic program to determine when to bid during the auction. Now, let me show you an example of that. Here's an example. So once you relax the assumption that all of these players are perfectly Bayesian players, there is a value to learning in the auction. So let me convince you that now, if you're not playing perfectly rational players, you want to learn, you want to bid early, because if you wait and snipe, you might end up overpaying. You might find out that you just happen to be in an auction where other players didn't bid that much, and you can end up winning the auction for less. So what I'm showing here are some value functions, the W functions, as a function of your bid, as a function of your previous high bid. So suppose you bid 4,093 and it's the last second of the auction, and you have a high bid already in the auction of 4,093, and you find out that you're the high bidder. So this 120 there denotes the last second, 1 means you're the high bidder, and 4,093 is your own high bid. That function is right there, and what it's saying is it's completely downward sloping. You don't want to improve. You could increase your bid, but increasing your bid means you're very unlikely that someone's going to beat you. So it's only if you had that really high bid, you feel like you're very, very likely to have won. Now, if you didn't know that much information, the black line shows you if you had a bid of 4,093, but you weren't the highest bidder, you don't know how much higher it would take to win. So now you want to go, here's your bid at 4,093. It's going to calculate that you should bid, a higher than 4,093 to win. Well, now, so you're going to bid higher because of the lack of information, and your expected gains are going to be less. And finally, if you're a bid sniper, given your information, your prior information, you would bid even higher because you have no information, you're uninformed, you're going to bid close to 5,000, and your expected gains from that auction, if you waited, is less. So in other words, there is a value. What we can generate is rationalize value for early bidding in an auction because of less than perfectly Bayesian learning. So incomplete or not fully rationally learning is enough to generate some value to early bidding. Now, the problem is, here's my last slide. I'm going to show you that it's not enough. So that alone was not enough. So we also had to do something that Chris Sims calls rational inattention. Now, what rational inattention is that think about a 2-minute auction, and somebody talks to you or your wife calls you, and you pick up the phone, and it takes several seconds. So you rationally know that sometimes you're gonna smoke a cigarette or you have to go to the bathroom. You're gonna be gone for some parts of the auction. You're not paying attention. Now, when you know that, and it's rational in the sense that you know that you're going to be distracted and not following the auction second by second, that means that if you know, like at second 110, you may be distracted for 5 seconds. That might mean that if you are paying attention at second 110, you should put in a bid there because just to hedge the chance that you might be distracted. So what we did is enter a cost of bidding and this rational inattention, and we added these parameters, and we have this anonymous equilibrium. And here's what we get. The red line is the average high bid track for the humans. And this is what our model predicts. Okay, so it kind of gets the early bidding in the first seconds of the auction, but then it falls below. So what we say is we're giving rationality its best shot, but we still cannot explain these early overbidding. The early overbidding is this gap. And so what do we have to do? If we want to have this model explain the bidding in these auctions, we got to do something else. So what's the, I'll stop here. It's time. We're going to now allow for irrational expectations, okay? We're going to drop, we're assuming that, people know this mean bid track. Well, now what we're going to do is maybe they're over optimistic. Their beliefs are actually above the red bid track. And then if we have their beliefs be higher, their actual collective behavior might start to match the red actual bid track. So what we then have is evidence here of irrational expectations that is costly to the bidders and it's costly to the auctioneer. What we show in the last slide, I'll promise right here, is if we get rid of this dynamic auction and go to a second price or a first price auction, the efficiency goes up to 100%. The winning bid goes up a lot, so the auctioneer wins, and the bidders actually make more profits as well. So it's a win-win. By eliminating the inefficiency of the dynamic auction, we can actually create a win-win situation for both the bidders and the auctioneer. End of story. So sorry for going over. Okay, well, thank you for coming, and I'm really again sorry I can't be here. And good luck and have a safe travels going back.